So when your circuit becomes more complex and becomes larger circuit, then sometimes or many times it is just not practical to solve using um, loop analysis or nodal analysis or mesh analysis. Yeah, because you will end up with so many equations within the system of equations. Of course, using computational method, you can solve those things quite quickly. However, sometimes while deriving the equation itself, it is not that easy, right? So while many times the questions related to the circuit only ask you some certain electrical parameters within limited part of the whole circuit. So you do not really need to calculate every single nodal voltage, for example, or every single loop current. So in that case, then these two theorems, Thevenin's and Norton's theorem, can provide you with a tool, with an advanced tool to do analysis in such complex structure, because they permit to hide information that is not relevant. So then you only concentrate to which part of the circuit that is important for your analysis. Okay. So for example, like now, like here in this shown circuit, this is a low distortion audio power amplifier. So it has this input from pre-amplified voltage, okay, and the output here goes to the speakers. And for example, if the question is, what is the voltage that is the output voltage coming out from this amplifier? What is the power that is supplied to the speakers? Then it would be so tedious and so complex if you need to solve every single node voltage or every single loop current within this circuit. So what we can do is we can hide the majority of the circuit and replace it with the corresponding what do you call it, equivalent circuit, and then we can calculate uh, the concerns or the important parameter being asked. Yeah, this is the whole circuit. To match speakers and the amplifiers, we need to analyze this circuit. So here, the whole amplifier can be replaced by an equivalent voltage, independent voltage source in series with loading or series resistance. Okay, so this is called as the Thevenin approach. If it is independent voltage source in series with series resistance, it is called the Thevenin replacement, Thevenin theorem replacement. So to match speakers and amplifiers, it is much easier to consider the whole thing, the whole amplifier as a simple equivalent circuit here. Okay. So the Thevenin's equivalence theorem states that a linear circuit may contain independent and dependent sources with their controlling variables as part A, connected to a linear circuit that may contain independent and dependent sources with their controlling variable also as part B. So here, part A has an output voltage of VO here and supply current I towards the terminal A and B, yeah, according to the passive sign convention. So the Thevenin equivalent circuit for part A here can be drawn like this, can be drawn as a single independent voltage source in series with a Thevenin equivalent resistance or RTH, yeah, supplying V output with the current I towards the linear circuit B, with current I entering to the A terminal and going out from the B terminal. So VTH here is the Thevenin equivalent source and RTH is the Thevenin equivalent resistance. On the other hand, we can also replace the linear circuit part A into an equivalent current source in parallel with an equivalent Norton resistance. Okay, so this is what is called as the Norton's equivalence theorem. Okay, so this is supposed to be Norton, yeah, not Thevenin. Norton equivalent source. This is also Norton equivalent resistance. Okay, so then let's have an example here of valid and invalid partitions. So in order that we can hide or we can change some parts of the circuit into equivalent voltage, independent voltage source and resistance, we have to choose carefully which part can be replaced by an equivalent voltage source and in series with resistance in the case of Thevenin equivalent theorem, or an independent current source in parallel with a resistor, Norton resistor, yeah, in the case of Norton's theorem. So for example, this is valid, yeah. So here it's valid, this is also valid, and this part is also valid, yeah. So proof, yeah, of this theorem. So circuit A is linear and it supplies current I towards circuit B and connected in at both terminal A and B. Okay. So if we consider circuit A is linear, the circuit B can be considered as a voltage source according to the passive sign convention, right? So if circuit A is unchanged, then the current I should be the same for any V output here, for any output voltage here at the terminal A and B. Yeah, if there is no change inside the circuit A, the supplied current I should always be the same. So by using source superposition, remember the superposition theorem that we had discussed last week. So what is the current I? Yeah, IO, yeah, here. So first is we set all independent sources set to 0 in A. Okay, independent sources here means the voltage source is short-circuited, the current source is open-circuited. Okay, so then we have IO flowing due to the contribution of the V output here. Then plus when this V output, the contribution due to the all independent sources in A. It means when the output is being short-circuited. Yeah, when we short-circuited this, then the contribution to the current flowing through this circuit is called as I short-circuit or ISC. Okay, so from here, the total current equals to the current when all independent sources in the circuit A is set to 0, which means that if it is voltage source, it is short-circuited, and when it is current source, it is being open, it is being cut open, plus the current when the connection between A and B is short-circuited. So here, from here, we can define Thevenin equivalent resistance as P output, yeah, divided by I output. Here, yeah, V output divided by I output. Since the current is coming out, yeah, from the Thevenin resistance in series in A, so that's why the sign is negative here. So here the current I equals to we replace IO with V output divided by RTH. So negative VO divided by RTH, yeah, from here, plus I short circuit, the current at short circuit for every V output. So the special case is when the current is when the circuit is open circuit, when the I is 0, so it means V output equals to the V output here across A and B equals to the V open circuit. So here there is no current flowing, I equal to 0, yeah, I open circuit, equals to negative VOC divided by RTH plus ISC. So from here, RTH, the Thevenin resistance, can be calculated as equals to the open circuit voltage. So when we cut this out, yeah, so no nothing. So basically, open circuit voltage is when this is cut out. Okay. So it means it's just floating. That will be the voltage at open circuit condition divided by I short circuit, the current when it is short circuited. Okay, so then the short circuit current will be equals to the open circuit voltage divided by the Thevenin resistance. Then the putting back into this equation, the total current will be first is from negative V output divided by RTH plus ISC, or V output here will be equals to VOC. Yeah, VOC is this part. Yeah, VOC equals to ISC times RTH, right? So if we multiply with ITH, so this becomes VOC negative RTH times current. Okay, so this is the formula. So how do we interpret this result? So because of the linearity of the models, for any part B, the relationship between the output voltage VO and the current I has to be the form V output equals to the constant M times this I plus N. Okay, so N is another constant. The result must hold for every valid part B that we can imagine. If part B is an open circuit, then the current will be 0, right? It means if current is equals to 0, then N equals to V open circuit. Okay, so because this is open circuited. So open circuit means that this is A, you have only like this. So this is V open circuit, no current flowing. Okay, then if part B is short circuit, so in that case it will be something like this, short circuited. Okay, so this one, the V output equals to 0. Yeah, here V output will be equal to 0 because it is short circuit. So in that case, here 0, V output equals to 0 when it is short circuit equals to M times I short circuit plus N, and we know N equals to V open circuit. So here 0 equals to M times I short circuit plus VO circuit. M equals to negative VOC, yeah, divided by ISC. So M here is the negative, the value of the negative of the Thevenin resistance, Thevenin equivalent resistance. So having found this, then we can insert this back to this equation. Yeah, V output equals to negative RTH plus the current plus the V open circuit. Okay, so the total V output here is similar to the previous version 1 of the proof. First is the contribution of due to the open circuit when B is open circuited, and then contribution of the voltage when the part B, so B is being short circuited. In that case, the output will be negative RTH times I. So, okay, so V output equals to minus RTH times I. plus VOC, V open circuit for any circuit in part B. So this is basically, we can draw this as an electrical circuit like this, right? The output here, remember, Kirchhoff voltage law using loop analysis. So if we look, use loop analysis here, yeah, negative VOC plus I RTH, right? Plus VO equals to 0. So VO equals to negative RTH I plus VOC, okay? Based on the loop, in this loop, yeah, Kirchhoff voltage law. So, and that is why this part can replace the whole circuit in part A, connected to part B. So this is the derivation of, we call it Thevenin's theorem. Okay. This is the Thevenin equivalent circuit for the circuit in part A. The voltage source here is what we call as the open circuit voltage, yeah? Which is the value we obtain by open circuiting the part B, okay? And it is called as the Thevenin equivalent source. The resistance RTH is calculated by short circuiting the part B. Okay, so it is called as the Thevenin equivalent resistance. Norton approach is basically similar, but now we are changing the whole part A circuit into an equivalent Norton current source and an equivalent Norton resistance. Okay. So here V output from the previous slide, V output equals to VOC negative RTHI, or the current here equals to VOC negative VO, right, divided by RTH, this value. This is the current flowing. So then V open circuit divided by the RTH from the previous derivation, we know that basically this is the short circuit current when P is being short circuited. Okay, so so basically this is a superposition as well. So this equals to let's see here. Yeah, so this equals to I equals to ISC negative the output divided by RTH. Okay, or this is the short circuit current and this is the open circuit current. Yeah, the contribution when it is open circuited. So when we put in equivalent circuit, it will look like this. So this is basically the I here equals to the I short circuit here, okay, plus negative V output divided by RTH, okay, divided by RTH, because this value, the current here is here like this value. Yeah, this is the current flowing here in this direction is V out divided by RTH. So I equals to ISC negative this VO divided by RTH. Okay, from Kirchhoff current law. Okay, remember? Okay, then let's continue. This is basically the Norton equivalent representation of for part A. So the Thevenin, the Norton equivalent resistance is basically the same as the Thevenin equivalent resistance. The short circuit current or the Norton equivalent current source is obtained by dividing the open circuit voltage source or the Thevenin voltage source by the Thevenin equivalent resistance or the Norton equivalent resistance. So IC is the Norton equivalent source, RTH is the Thevenin equivalent resistance or Norton equivalent resistance. They are the same. The value is the same. So another view of Thevenin's and Norton theorem. So this is Thevenin, well, this is Norton. This equivalence can be viewed. Yeah. So the relationship is as before. So ISC here equal to VOC divided by RTH. Or VOC also, if you first calculate ISC, can be calculated, VOC can be calculated from ISC times RTH. Screw down the same. Any questions so far? Okay. This equivalence, okay, clear drawing first. This equivalence can be viewed as a source transformation problem. It shows how to convert a voltage source in series with a resistor into an equivalent current source in parallel with the resistor. Source transformation can be a good tool to reduce the complexity of a circuit. Source transformation is a good tool to reduce the complexity of circuit when it can be applied. Ideal sources are not good models for real behavior of the sources. Yeah. A real battery, for example, does not produce infinite current when short-circuited. Why is it like that? Because it actually has an internal resistance as well. Here. Yeah. So actually, a voltage source like a battery is not just an independent, it doesn't only contain the independent voltage source, but actually it also contains an intrinsic resistor, yeah, an intrinsic resistor. Because when it is short circuited, there is always a current, right? Because if there is no such resistor, the current will be infinite, and because resistance is zero, voltage divided by zero will be infinity, right? Well, in reality, no such current exists. There is always some value of the current. So it means there is an internal resistor value inside that voltage source. Similarly, with a current source, an independent current source, actually there is a parallel resistor. Because if there is no such parallel resistor, when it is short-circuited also, the voltage will be infinity. When there is a resistor here, the voltage will be equals to the current here multiplied by this resistor. So the models are equivalent when this RV equals to RI equals to R. Vs equals to Is times R. Yeah. Source transformation can be used to determine the Thevenin or Norton equivalent. Although there may be some more efficient techniques to transform the source. Here, an example, we have the circuit containing one independent voltage source, 12 volt, then another one, an independent current source, 2 milliampere. So there are some set resistors there. So this one basically can be replaced, right? This is an equivalent. We can replace this into an equivalent current source with a parallel resistor. Yeah. From Thevenin, change into Norton equivalent circuit. So in between the terminals we output here, we connect a current source and a resistance in parallel. The equivalent current source now, here, if we change this into a current source, the value of the current will be 12 volt divided by 3 kilo ohm, which is how many? 4 milliampere, right? Then the 3 kilo ohm and the 6 kilo ohm can be combined because they are in parallel. So like this. So we replace this with one single 4 milliampere. 3 kilo ohm and 6 kilo ohm becomes a parallel resistor. Yeah. So 3 times 6, 18 divided by 9 is 2, becomes 2 kilo ohm. So from here, then we have this a series resistor. So we can further transform this current source in parallel with the 2 kilo ohm into an independent voltage source in series with this resistor also. So from Norton representation to Thevenin representation. Yeah, so the equivalent voltage source will be 4 milliampere times 2 kilo ohm or 8 volt, right? In series with a 2 kilo ohm resistors. So the 2 kilo ohm resistor in series with this 2 kilo ohm can be combined into a single 4 kilo ohm. Now it is connected again with 2 milliampere current source. So we can replace this circuit again with an equivalent current source and a parallel resistor. Okay, the current source value will be 8 volt divided by 4 kilo ohm equals to how many? 2 milliampere, right? Then that 2 milliampere is combined with this current source. Remember the principle of superposition, combination of source, so becomes 4 milliampere source, and the resistor is 4 kilo ohm in parallel with that 4 milliampere current source. So from here we can do again source transformation into an independent voltage source in series with the 4 kilo ohm. Otherwise, we can already solve, do another source transformation, get a single loop circuit, or we use current divider formula because here this one can be is in series. Then from there we can calculate I/O, right, using current divider formula. From I/O, then we can calculate the output by multiplying that I/O with 8 kilo ohm. Okay. Let's have this as example. Compute V output using this source transformation. Here we have Vs R1, R2, Vs2, R5, Is, R3, R4. So first transform this Vs and R1 into a current source, okay, into a current source and a parallel resistor, okay. And this one is a voltage source. So from here we can replace that into a current source. Yeah. How? So this becomes Vs because this is in series with this, right? It can be replaced. A series resistor with an independent voltage source can be replaced by a current source and a parallel resistor. So this is replaced into a current source here whose value is Vs2 divided by R2 in parallel with R2. So from here, this Vs1, this current source can be added with this current source. Then this parallel can be also combined as a parallel resistor. Okay, but this it can be further combined the current source with the other current source in parallel here, Is, and the resistor in parallel R5 can also be combined with R1 and R2. So this become a single equivalent current source with an equivalent parallel resistor now in series with this R3 and R4. So to calculate the output, there are two options. First, we can use current divider formula. Yeah, now it is simple enough already to use current divider formula. Alternatively, we can transform again this parallel equivalent current source and resistor into an equivalent voltage source in series with a resistor. Okay, then use voltage divider formula. So so this one is I equivalent here equals to the Vs1 divided by R1. Yeah, this is the value from this part there. And R equivalent here is the parallel of R1, R2, and R5. Okay. So this is I/O. We can, for example, transform again. We choose another source transformation. So from here, we replace with an equivalent voltage source in series with this equivalent resistor. Yeah, then the equivalent voltage source value equals to this I equal the value of this equivalent current source multiplied to the equivalent resistor. Yeah, while the equivalent resistor in series with this voltage source is still the same. So from here we can calculate V output using voltage divider formula, R4 divided by R4 plus RQ plus R equivalent times V equivalent. Okay, so simple enough, right? So using this Norton and Thevenin equivalent resistance, we can simplify a long big circuit one by one. Yeah, something like that. So this equivalent voltage source becomes the Thevenin equivalent voltage source, while this equivalent resistor is the equivalent Thevenin resistor. Okay, so basically we can a voltage source in which previously we always draw as an ideal independent voltage source without any internal resistance. We can improve that model as a voltage source in series with a internal resistor. Otherwise, we can also replace the current source with a more improved model as a current source in parallel with an internal internal resistor. Yeah. So the two models are equivalent when RV equals to RI equals to R, and this Vs voltage source equals to Is times Ri, or Is equals to Vs divided by Ri, or divided by Rv. Source transformation can be used to determine the Thevenin or Norton equivalent. We now review several efficient approaches to determine Thevenin or Norton equivalent circuits. So what will be the general procedure to determine the Thevenin equivalent when we are given a big circuit? Basically, first is to determine the V open circuit. When the circuit at the terminal is being cut, yeah, so the load is being taken out, so it is now hanging as an open circuit. So then we determine that voltage at that ends, which becomes the open circuit voltage, and that open circuit voltage will become the Thevenin equivalent voltage source. Yeah. So VTH, or open circuit voltage, is the voltage at the terminal AB when part B is being removed. Secondly, we determine the short circuit current. That is when part B is replaced by a connecting wire, short circuiting it. So that current ISC is obtained, and then the Thevenin equivalent resistance can be calculated from the VTH, or the open circuit voltage, divided by that short circuit current, and then to get the Thevenin equivalent resistance. So first, determine the Thevenin equivalent source by removing the part B at the N terminal, making it open circuit, and determine the voltage at that two terminal, voltage VAB, which will becomes V open circuit. Okay, that's VAB. Then number two, we short circuit that AB terminal. We remove part B and then we short circuited it, and then calculating that current, that short circuit current, IAB or ISC. From there, then we can calculate the Thevenin resistance, VAB divided by IAB, yeah, or the RTH, or the V open circuit divided by I short circuit, and the Thevenin equivalent voltage source equals to the open circuit voltage value. An example of determining Thevenin equivalent. So we have an independent voltage source in series with R1. Then there is another independent current source IS in parallel with R2. And this is connected to part B, the load. So part B is relevant. The voltage VAB will be the value of the Thevenin equivalent source. So first, what is the efficient technique to compute this open circuit voltage? here. So this is the will become VTH. Using node analysis, okay, this node VTH divided by R2, VTH minus VS divided by R1, not minus IS. IS is coming in equals to 0. Yeah, get node analysis is Kirchhoff voltage, Kirchhoff current law. The node analysis first. This is at node here, not this at this node VTH. This one at this node first. Then the second node is oh yeah, from here we can first simplify, yeah, 1 over R1 plus 1 over R2 VTH. Yeah, then Vs coefficient is put to the right hand side of the equation, plus Vs divided by R1 plus Is. Then from here we obtain the VTH equals to this one all divided by this one, which is R1 plus R1 R2 divided by R1 plus R2. Here we obtain R2 divided by R1 plus R2 Vs plus R1 R2 divided by R1 plus R2 times Is. Then we obtain VTH, or simplified further, this becomes R1 R2 divided by R1 plus R2 Vs divided by R1 plus Is. We obtain the Thevenin equivalent voltage source. Then we calculate the short circuit current at this PB. Okay, when it is short circuited so that then later we can calculate the Thevenin equivalent resistance. Okay, what is the short circuit here? We can try using superposition, yeah, that we have learned last week. So first, the source is being opened. Yeah, this is made open. When the current source is open, then the current through this short circuit will be this Vs divided by R1, right? So let's draw again. So this one is when current source is open, so the circuit becomes like this. And this is short circuited. Okay, this is R2, this is R1, this is Vs. Okay, no current flowing through this R2, right? Because this is short circuit, all the current will flow through this one. This will be the ISC. So ISC equals to Vs divided by only with this value. Yeah, be careful. Don't get confused.
Sir.
Yes.
The current source also missing. Yeah? We also erase the current source. Yeah.
Which one? In this one? This part?
Yes. Yes.
Huh? Yeah, because now we are using superposition. This is not finished yet.
Oh, okay.
This is not finished yet. Yeah. This is ISC 1, right? This is ISC 1. It means this is the short circuit current due to the contribution of the voltage source. Not finished yet. Patient. Now we calculate the current short circuit current as the contribution of the IS. Okay. So in that case, we short circuit the Vs. Okay, we make remember superposition, yeah, last week. So you have to understand last week lesson in order that you can understand now. So second contribution due to the IS is calculated by short circuiting Vs. Okay, so if this is short circuited, then what happened? So if you are in doubt, always redraw. So this is short circuit. So this is R1. This is IS. Like this, right? So what is the current now? The current here, ISC2. This is ISC2. The current due to the current source. Of course, Yeah, this is basically a current divider. What do you call it? Current divider formula, right? So the current flowing through here, all the current ISC will go through this one, right? Because this resistor here is 0. The current divider formula states that let's say this is R1, this is R1, this is R1, R2. When you have in Kirchhoff current law, when you have a branch which does not have any resistance, 0 resistance, of course all current will flow through that branch. No current will flow in this and in this branch. Okay, so this IR1 will be 0, IR2 will be 0. So ISC2 will be equals to IS. Understand? If it is short circuited, that is what will happen. So now total ISC will be this plus this. Yeah. So ISC, the total short circuit current will be equal to IS plus VS divided by R1. Then, so we obtained already ISC. Previously, we obtained this VTH. So the Thevenin equivalent resistance can be calculated VTH divided by ISC. Okay, or this divided by this. So this factor is gone, so becomes only this part. R1, R2 divided by R1 plus R2. So for this case, the Thevenin resistance, this particular can be computed as the resistance from A to B when all independent sources have been set to 0. Yeah, this is one of the, later we will see in the example, one of the short way to calculate RTH. So if we redraw again, the circuit, when all the sources are set to 0, when all the sources are set to 0, so it means how will it become? So let's shape this one. Okay, let's close this one first, so that then we have more space. So this source is mid 0, so it is short circuited. This is R1. This source IS is mid 0, it means it is open circuit. Then we have R2, right? This is R1. So then this is A and B. So RTH, we can calculate like this. ISC, short way would be to immediately find the equivalent resistance between A and B. So this R1 and R2 are in parallel, right? So RAB equals to R1 R2 divided by R1 plus R2. Okay, so this. Okay, so Thevenin resistance can be computed as the resistance from A to B when all independent sources here are set to 0. So for current source, it is made open. For voltage source, it is made short circuited. Okay, so let's take a break. It was already 15 minutes. Okay, one moment. First is save this. Clear on the drawing. Then